4.5 is the last section that will be on your second exam. It is getting information from my model. So this is kind of the ultimate thing we've been trying to get to in chapter 4, and that is solving equations that involve exponentials and logarithms. So if I gave you an example like 3 to the x equals 5, solve for x, you want to be able to actually solve this. So now that you have all of these tools available to you, you know the laws of logarithms, you know how exponentials and logarithms are related, you know how to pull that x down out of the exponent and actually solve for it. So you want to take a log of both sides. We have log of 3 to the x is equal to log of 5. Then that pulls the x down in front using your laws of logarithms. So you have x times the logarithm of 3 is equal to the logarithm of 5. And so x is just log 5 over log 3. Right? That's about 1.464974. And you can verify that with your calculator. This is the stuff you were already doing. That's why this example was clear from the start. Because you've been doing this. You probably would have defaulted to log base 3. Why did I use log instead of log base 3? Because at the end of the day, if you're calculating log base 3 and you don't have log base in your calculator, then you couldn't do that. You would have to use log. So I want you to get in the habit of applying your laws of logarithms every opportunity, because that's the thing that, especially when students go on, sometimes you forget all of those and you really do need them if you're solving problems involving these. So I just want you to get in the habit of using them. Let's do some more. So if I said solve algebraically using exponentials and logarithms for 2 to the x is equal to 3 times 5 to the x. Okay, so now I have a lot more going on. I take a logarithm of both sides. Log of 2 to the x is equal to log of 3 times 5 to the x, right? That's consistent. I'm doing it to both sides. Now I apply laws of logarithms. So my x in the exponent is going to come down. Here, I have to split this multiple because 3 isn't being raised to the power x, but 5 is. So I have to split those up first. So I have x log 2 is equal to log of 3 plus log of 5 to the x. Now I can move that x down in front, all right? So I'll have x log 2 is equal to log 3 plus x log 5. Get all of my x's on the same side, so I'll subtract the x log 5 from both sides. And then I'll pull the x out of that. So I have x times log of 2 minus log of 5 is equal to log of 3. And then I just divide both sides by whatever constant is log of 2 minus log of 5. So I divide by log 2 minus log 5, and I have that x is equal to log of 3 over log of 2 minus log of 5. I can simplify this denominator a little bit, because I know that subtraction corresponds to division, and so that's log of 3 divided by log of 2/5. You don't have to do this in your simplification on an exam necessarily, but it's important that you recognize these laws of logarithms. If I was asking you to compress it as much as possible, then yes, you want to do that, but if I'm just asking you to solve for x, it's a different question. So when I was asking you to put it into one logarithm, that's the kind of thing you would do there. This obviously cannot be reduced to one logarithm. You still have a log divided by a log, so you're stuck. There's nothing you can simplify more. That's as simplified as it'll get to compress it into one thing. Now, let's look at a logarithm example. So that started with an exponential. Let's look at one that starts as a logarithm that we have to then convert. So if I have log base 3 of x minus 2 is equal to 4 as the problem, what is the first thing that I'm going to do? Since I'm starting with a log base 3, the only thing I can do is take 3 and raise it to the power of this log base 3, so I can invert it. So I take 3 to the log 3 of x minus 2 is equal to 3 to the 4. So I make both sides of that equation my exponents for a base of 3. And then from there, because the log base 3 and the 3 to the log base 3 part, that whole thing cancels to a 1. I end up with just the x minus 2 that's inside of the logarithm is equal to 3 to the 4th. 3 to the 4th is a constant that I can solve for. It's going to be an integer too, so that's something I actually want to do. 3 to the 4th is 81. Then I just need to move the 2 over, so I add 2 to both sides, and I have that x is equal to 83. Not bad. Let's do another one, because these are weirder, I think, from what you've been used to doing. What if I give you log base 2 of x plus 3 equal to 5? Again, I was given a base, so I have to use that base. 2 to the log base 2 of x plus 3 is equal to 2 to the 5. The log cancels with the base 2, and I'm left with x plus 3 is equal to 2 to the 5th, which, again, is a constant. That's an integer, 32. Then I just need to move my constant over, minus 3 from both sides. I have x is then equal to 29. Let's take this a step further where it's a little bit more abstracted and you can't just immediately use the base. So if I gave you natural log of x plus 1 minus natural log of 4 is equal to 2, I have to combine the logarithms before I can use the base to get rid of the logarithms. So I have to realize that the subtraction corresponds with division and rewrite this as natural log of x plus 1 divided by 4 is equal to 2. Now that I just have one logarithm on that side, I can use that base, which again from last section we know is base e. E to the natural log of x plus 1 over 4 is equal to e to the 2. So then I have x plus 1 over 4 is equal to e to the 2. Solve for x. Now it is your normal algebra. Multiply by 4 on both sides, and you have x plus 1 is equal to 4e squared. Subtract 1 from both sides, and you have x is equal to 4e squared minus 1, which you can plug into your calculator now. I don't recommend doing it prior to this because you will run into round-off error. Now, or just rounding error, because you won't be able to give it the infinite decimal places, but it can do it itself for how it's stored in the calculator, and it'll be more accurate. So 4e squared minus 1 is about 9.87313. Okay? We also have applications to talk about, so this video is going to be longer than the last. Population and investment models is the first of those. We want to actually compare how these models, like what is the interest that you accrue depending upon which model you use. We did a little bit of this in the last section. So if I want to invest $3,000 in an account accruing 4% interest, how long will it take for it to reach $4,000? The reason that I'm using this as an example is just so that we can compare them in another way, but it's a very similar problem. The old way, if it's accruing 4% interest annually, so if we compare compounding it annually, then we have 4,000 is equal to 3,000 times 1.04 to the x. Okay? Divide both sides by 3,000 because we're solving for x. And you have 4/3, which I'm not writing as a decimal because the 0.33333 goes on forever. Now 1.04 to the x. If I take a log of both sides, I have log of 4/3 is equal to log of 1.04 to the x. Now that I can reduce again, remember that exponent can come out in front. And then I have log of 4/3 is equal to x times the log of 1.04. To solve for x, I just need to divide both sides by log of 1.04. And we have that x is equal to log of 4/3, which is the same as log 4 minus log 3, over log of 1.04. This is approximately 7.335 years. What if we compounded it monthly instead of annually? Then you just change your old model, so you divide by 12 and you take it to a 12t. We do the same things, divide by 3,000, take a log of both sides, and then you end up with log of 4/3 is equal to 12t log of 1.0033333333. It goes on forever. Now, just to solve for t, you divide by that 12 log of 1.00333333. Then if you simplify that expression, right, if t is equal to log of 4 minus log of 3 over 12 log of 1 plus 0.04 divided by 12, you should get 7.204 years approximately. So we see some decrease because it's compounded more frequently. We also did compound it daily. So then, right, the 365, we use the same process, 4,000 equals 3,000 times 1 plus 0.04 divided by 365, raised to the 365t. And then you can divide both sides by 3,000, take a logarithm of both sides, just like we did previously, to get your same log of 4/3 is equal to 365t, log of 1 plus 0.04 divided by 365. Solve for t. And if you plug that into your calculator, you should get about 7.19245 years. So you'll see that this is steadily getting to be a shorter period of time. So it should be an even shorter period of time if we compound it continuously. If it's compounded continuously, we have 4,000 equals 3,000 e to the 0.04t. And in this case, right, we will have 4/3 equals e to the 0.04t. We can just take a natural log of both sides to invert that e. And then you'll have natural log of 4/3 is equal to 0.04t, getting us 7.19205 years. So you'll notice that it got less and less and less with each stage. And so it's important to just notice that the more frequently that you add your interest, the less time you have to wait for it to reach a certain value. Some circumstances that's going to be more obvious than others. I mean, 4% isn't a huge increase, so it doesn't make a huge difference in the number of years. In fact, 7, if we rounded all of these, they'd all round down to 7 years. So it's not a huge difference if the percentage is very small. It doesn't change that. One more application, Newton's law of cooling. This is important since it has to do with, things you do on a daily basis, maybe like make a cup of coffee or a cup of tea, and then you leave it on the counter and it cools and then it feels cold. You can model how that temperature changes through Newton's law of cooling. So the equation that we have here, T equals A plus I minus A times E to the minus KT, you have T is the temperature of that particular item, say your coffee or your tea. I is its initial temperature, so when you first poured boiling hot water into that mug, that's the temperature of that water. A is the ambient temperature, which means that's the temperature of the room that it's in, where, when it's sitting on the counter. And then K is a heat transfer coefficient that tells you effectively how quickly is this going to cool. So it makes sense because if you wait forever, right, as t goes to infinity, e to the minus kt will approach 0. And so this will all cancel, leaving us with just the ambient temperature. And that makes sense. If you leave it on a counter in a room where it's cooling, it's never going to go below the temperature of the room at all, right? And then the I minus A here is so that when t equals 0, e to the minus kt gives us 1. And so we have A plus I minus A, which means that we should get our initial temperature back at 0, right? So let's look at an example of a stew pot. Say you cooked a pot of stew up to 160 degrees Fahrenheit. In a room that is currently 68 degrees Fahrenheit, we'll assume that that's evenly distributed, and a heat transfer coefficient of K equal to 3. Determine how long it needs to cool before it reaches 80 degrees, so that you could put it back in the fridge. So the initial temperature is that 160. The temperature we want it to reach, T, is that 80. K was given as K, as 3. And the ambient temperature is given as 68 degrees. So we want to figure out how long it's going to take. We use the equation that was given, T, which is 80, is equal to A, which is 68, plus the difference between I and A, 160, which is I, minus A, 68, times E to the minus KT. And since K is 3, we have minus 3T. Then we just need to solve this equation for t. So first thing we're going to do is subtract that 68 from both sides, right? Because that's the additive constant at the end. And so we have a difference of 12, and then 160 minus 68 gets us 92. So we have 12 is equal to 92e to the minus 3t. Divide both sides by 92, and that reduces to 3 over 23 is equal to e to the minus 3t. How do we get rid of the e? Natural log of both sides. So we have natural log of 3 over 23 is then equal to natural log of e to the minus 3t. And those two will cancel each other, leaving us with a negative 3t being equal to natural log of 3 over 23. To solve for t, we just need to divide both sides by that negative 3. And so we have a negative 1/3 natural log of 3 over 23 is equal to t, which, if you plug that into your calculator, gets you 0.678961 hours, since everything was in hours. And then that corresponds to about 41 minutes, if you were to think about it. And that makes sense. You might take stew 41 minutes for it to cool if you leave it on the counter. Okay, the very last application, radiocarbon dating. This is a model of exponential decay. And so specifically we talk about it in terms of the half-life. So when we talk about radioactive material, we typically talk about it in terms of its half-life, which is why the model for this is going to be c times 1/2 to the t over h. So if the half-life is defined to be a certain amount of time, then how much of a particular half-life has been reached will be defined by t divided by h, where h is the length of that half-life. And then we're using that a value of 1/2 because it's going to decay by half after that time. So when t over h equals 1 half-life will have occurred, and the quantity of our substance will have been cut in half or multiplied by 1/2. So if c is your initial mass, h is the half-life, and m is the mass remaining after time t, this is our model. Let's look at an example. If we have a half-life of cesium-137 of 30 years, so that means t will be in years, set up the model for a 30-gram sample. So m of t, we use our model, we're starting with 30 grams, so 30 times 1/2 to the t over 30 years. So you can define your growth factor by taking a look at what that would be raised to the t, because your growth factor is a, right, a to the t in the model. So 1/2 raised to the 1 over 30 is actually our growth factor, which in this case is actually decay, but not growth, but that's fine. So we end up with 30 times that 1/2 to the 1/30th power raised to the t. When will there be 25 grams left? So this model, where I'm talking about the growth factor up here, is really just to relate it back to exponential models that you had dealt with before. But ultimately it's still the same. You just have to keep track of how long is the actual half-life. It relates what we talked about from 3.2 when we were changing the time periods to specific application. So 25 grams left. 25 is equal to 30 times 1/2 to the t over 30. Okay, so divide both sides by 30. We have 5/6 is equal to 1/2 to the t over 30. If we take a logarithm of both sides, we have log of 5/6 is then equal to log of 1/2 to the t over 30. We can simplify this one because the exponent goes out in front, and we have log of 5/6 is equal to t over 30 times the log of 1/2. So we can just solve for t now algebraically. Divide by log of 1/2 over 30, which becomes 30 times log of 5/6 over log of 1/2, which is about 7.89103 years. So in a little under 8 years, it will go from 30 grams to 25 grams of material. Please let me know if you have any questions.